In this video, we will derive the element stiffness matrix for an axial force element starting from our previously derived potential energy formulation. This approach is more systematic than the previous method and can be easily extended for application to other element types. To begin with, we assume that every displacement is unknown. The minimum value of total potential energy results when we minimize, with respect to the displacement, our total potential energy function. Written mathematically, that is, the first derivative with respect to every displacement. So d pi du1 equal to 0, d pi du2 equal to 0, all the way up to d pi dup equal to 0. We can rewrite this equation in vector form to give d pi du, where u in curly brackets is a vector of displacements, and then all of these differentiation terms can be collected into a single vector, again denoted by curly brackets, d pi du1 d pi du2 d pi dup, and all of these are set equal to 0. Recall from the previous video that the total potential energy for a system of n elements is given by the following expression. Pi, which is total potential energy, for the system is equal to the summation over all of the elements E from 1 to n of the elastic strain energy, and we have the superscript E here to denote for each element, from which we subtract the work terms for the various loads from 1 to P, the work being the load times by the displacement caused by that load, and remembering that the load and the displacement act in the same direction. The derivative with respect to an arbitrary unknown displacement u beta is given by the following expression. d pi du beta is equal to the summation over the elements, differentiating our elastic strain energy with respect to the displacement u beta, and then we subtract the load p beta. So for a system of n elements and p unknown displacements, this gives the Bethe equation corresponding to displacement u beta. So for example, for a system containing n elements, the contribution of the beta of displacement to the strain energy is given by the following expression. Summation of E was 1 to n, the derivative of the strain energy with respect to the beta of the displacement, that's equal then to d lambda 1 with respect to d u beta plus d lambda 2 with respect to u beta, all the way to the final value of lambda, which is lambda n, again with respect to u beta. So what this means is there can be any number of displacements in the system corresponding to the number of nodes, and there can be a separate number of strain energy expressions corresponding to the number of elements. And in what we are doing, you have to differentiate with respect to all displacements every single element equation. If we recall from the previous video that for an axial force element, the strain energy in terms of nodal displacements Ui and Uj is given by lambda E, which is then equal to A times E over 2L multiplied by capital Ui squared minus 2Ui Uj plus capital Uj squared, from which we subtract A E alpha delta T minus Ui plus Uj. In this, we've actually ignored the final term that was derived in the last video, as it doesn't contain either Ui or Uj. What we can see here is that this expression is only a function of Ui and Uj. Everything else in this expression is a constant. From this then, we're able to conclude the following. We can conclude that the derivative of the elastic strain energy with respect to the beta displacement is equal to 0 unless beta is equal to I or beta is equal to J. So basically, if we are looking at an element which has two nodes, I and J, and each of these nodes can displace by a value of U beta, not necessarily at the same time, then if we differentiate the strain energy for this element with respect to U beta, it is only possible for it to have a non-zero value if beta, in this case, is equal to I, and in this case it is equal to J. So if I is equal to 1, then it would be U1, and if J is equal to 2, then it would be U2. If further down the line there were other elements which, let's say, had a value of K equal to, say, 3, then if we differentiate it with respect to any displacements here, then this strain energy expression for this particular element E would be 0 because this displacement does not feature in this element. So therefore, the contributions of displacements Ui and Uj to element E are given by the following expressions. We take a derivative of the strain energy with respect to Ui, because we know that this is non-zero, and that gives us AE over L times by Ui minus Uj plus AE alpha delta T. And then similarly, we differentiate with respect to Uj, and that gives us AE over L times by minus Ui plus Uj minus AE alpha delta T. So this is a system of equations, a pair of simultaneous equations, that lends itself to being written in matrix form. So we can make a column vector out of the derivatives here, and we can formulate a matrix vector system out of this here. So let's do that. So our vector of derivatives is given by d lambda e dui, d lambda e duj. We'll factor out the AE over L terms to get AE over L, and then a coefficient matrix containing ones. And this is then multiplied by a vector containing ui and uj, and then a final vector of constant terms, which are basically our internal element forces, minus A E alpha delta T, A E alpha delta T. Looking at this now, we can make the following definitions. The square matrix multiplied by AE over L is what we will refer to as our element stiffness matrix. This column vector of displacements are our element degrees of freedom, and then finally this vector on the end are the internal element forces. So in this case, these element forces are due to thermal loads alone. We can then rewrite this in more compact form by saying that the derivative of the elastic strain energy for element E with respect to all of the displacements associated with element E is given by the element stiffness matrix multiplied by the element degrees of freedom, which is a vector, from which we subtract the internal element forces. The equilibrium for the whole element is then written as the derivative of the total potential energy for the element with respect to the element degrees of freedom, and that's then equal to equation 10, which is d lambda E divided by d ue minus our vector of external nodally applied loads PE, where in this case PE is simply PI and PJ, which are the nodes applied to the element nodes. If we then assemble all of our elements, we then get the global stiffness matrix, global element forces, and global applied loads. So this gives us the derivative of the total potential energy for the whole system. So I've dropped the superscript e's to denote this, and that's equal to the system stiffness multiplied by the system degrees of freedom minus the system element forces and the system applied loads. And this is all equal to 0.